In image enhancement, there are mainly two techniques. One is spatial domain. In spatial domain, the processing is carried over directly on the pixels itself. So, enhancement carried in the image plane itself is called the spatial domain. On the other hand, in the transform domain, image enhancement is carried in transform coefficients, non-directly process intensity values of image plane. In spatial domain process, the input image is denoted by f of x comma y. We apply some transformation to obtain enhanced image known as g of x comma y. Here, the T is a window defined over a neighborhood of point x comma y. So this is the image in spatial domain. So in this we move a mask from top right to bottom left. The center of the mask is moved over each and every pixel and operation is performed. The operation may be either a low pass filter or a high pass filter. Image enhancement generally classified into three types. One is point processing, second one is local processing, third is global processing. If enhancement is performed directly on a pixel, then it is called point processing. Second, suppose if we apply a filter over a small neighborhood of an image, then it is called local processing. If image enhancement is applied to the whole image, it is called global image enhancement. In spatial domain process, for point processing, there are different techniques used. One is the intensity transformation function. In this, there is a gradual variation from the dark to light. So we have applied a thresholded image. In this, below the threshold, the image is considered as 0, and above the threshold it is considered as 1. Thresholding increases the contrast of the image. There are three basic point processing transformations. One is negative, the second one is logarithmic transformation, and third one is gamma power transformation. In image negative, the image S we can obtain by subtracting the pixel before processing from 255. Here L is 256. L is the number of gray levels used in the image. So in this, R is pixel before processing and S is pixel after processing. Logarithmic transformation mainly used in Fourier transforms. Generally, the images we capture with 8-bit camera. So the grayscale intensities of image range between 0 to 255. But when we take the Fourier transform, the dynamic range of the image lies between 0 to 2.5 into 10 to the power of 6. So because of that, the visibility is very poor in Fourier transformed images. To improve the visibility, we use logarithmic transformation for dynamic compression. Nth root is gamma transformation. Gamma transformation is mainly used in display devices like television monitors, CRT monitors, and TV monitors. The main problem with the display devices is they look more darker than intended to be. To improve that, gamma correction is a feature added in every television monitor. So log transformation, this maps a narrow range of low intensity values in the input to a wide range of output levels. The output is true for higher intensity values. We use such a transformation for expanding the values of dark pixels in an image while compressing the higher level values. So see, this is the Fourier transform of the image. The dynamic range of the Fourier transform of the image is 0 to 2.5 into 10 to the power of 6. So the visibility is very poor in normal display. So to increase the visibility, dynamic compression is performed by using the logarithmic transformation. In this, we have to highlight the major blood cells and study the shape of flow of the contrast medium to detect blockade. So in this, we used gray level slicing. So the main difference between the two is in the first image, threshold is applied. And here background is completely eliminated, but in the second picture what happens is the background is retained while enhancing the region of interest. Contrast stitching expands the range of intensity values in an image so that it spans the full intensity range of recording medium or display device. Highlighting a specific range of intensities of often is of interest. Contrast stitching. So this is a low contrast image. Power law transformation. Power law transformation have the following formula. Here gamma is the parameter we use. If gamma is less than 1, the image looks more darker than the original image. If gamma is greater than 1, the image looks more brighter than the image. So it maps a narrow range of dark input values into a wide range of output values, with the opposite being true for higher value of inputs. So this is the original image, but when we view on a monitor, see that the image looks more darker than the original image. So for making the image more like the original, we have to apply gamma correction. This facility is provided in televisions. By using the gamma correction, what happens is the image viewed on monitor becomes as the original. Here gamma is 5.0. So the image looks more darker than the original image. So this is the original image. We apply gamma 3.0. It is more darker than the original image. Gamma 4.0 still more darker, gamma 5.0 still more darker. So as gamma is greater than 1, the image looks darker than the original image. So if gamma is less than 1, the original image becomes brighter than the original. So this is for gamma 0.6 and this is for gamma 0.4 and this is for gamma 0.3. Gray level slicing. So the main intentions of gray level slicing is it highlights a specific range of gray levels similar to thresholding. Other levels can be suppressed or maintained. Useful for highlighting features in image. Bitplate slicing. Often by isolating particular bits of pixel values in an image, we can highlight interesting aspects of image. Higher order bits usually contain most of the significant visual information. Lower order bits contain subtle details. So in this, the image is generally captured with 8-bit camera. So the intensity levels of the image are between 0 to 255. So these image we can view as a 8-bit plane. So we generally divide the image into bit planes. So this is one sort of doing compression. Normally lower order bit planes contains the subtle information and higher order bits contain significant visual information. So instead of transmitting all the 8 bits, only will send 4 bits during transmission and storage. At the receiving end again we append the low order bits to reconstruct the image. So in image compression, this bit plane slicing is widely used. So this is most significant plane of image. This is the next significant plane of the image. Like this, see the first 4 bit planes contains the visibly significant information. Similarly, this is the original image. And these last 4 are the most significant bit planes, and the remaining 4 bit planes contains the subtle information. So next, histogram equalization. Generally, histogram is nothing but the probability density function of an image. In the next class, we are going to study about what is histogram equalization. Histogram generally tells whether the image is bright, light, dark, low contrast, and high contrast image. In histogram, H of Rk is Nk. Here Rk is the kth intensity value, Nk is the number of pixels in the image with intensity Rk. So generally the R ranges between 0 to 255. Suppose for 128 intensity there are 1000 pixels in the image. The total number of pixels in the image are 10,000. Then what is the probability of occurring the gray level intensity 128 is Nk is the number of pixels with the intensity level 128 and the total number of pixels is 10,000. So P of Rk is 1000 by 10,000, that is 0.1. In histogram, on the x-axis